Welcome back to second part of the High Performance Computing Advanced Scientific Computing course, Lecture 11, Deep Sequence Model for Computational Fluid Dynamic Application. In the first part, we talk about the background and history of the fluid dynamic and deep learning application, and also the long short-term memory variants from the neural network, recurrent neural network, and its capability to be used in the fluid dynamic area. In the second part, we will have some practical application of these models. So this is the second part regarding the deep sequence models. Uh, as we said in the first part, we need to think how we can apply the sequence deep learning in the fluid dynamic area, which is focused on the turbulent flow currently, how the data could be matched. We have Lagrangian perspective, which the velocity is spatial and temporal, which means the velocity is a function of the location and function of the time. This perspective and this framework could be great choice to use it for the sequential deep learning model. The next question is applying the raw data. In the fluid dynamic application, there are many devices which is used in the industry, and they are measuring the velocity or another parameter like the acceleration, the flow, and for example, for the heat transfer, we have the temperature and also the pressure, which these data could be applicable as a time series, like the flow meter, constant temperature anemometer, laser Doppler anemometry, pitot tube, light detection, and ranging. Is the raw data able to determine the flow feature? Our focus here about the turbulent flow. From the turbulent flow, it is well addressed that the statistics are applicable to describe the flow feature and the flow behavior. As we mentioned in the lecture 9, there was a statistic approach suggested by Taylor in 1935, and this is the fundamental of the statistics that are applicable in the turbulent flow. So we can use the measured data from the statistic approach for turbulent flow studies and use them maybe for the prediction or simulation. And to list the advantage of the deep learning approach from the recent literature and recent study, it's capable to extract the hidden information. It's applied in a various area, and especially for nonlinear and random phenomena, it was successful. One of the approaches convolutional network and also recurrent neural network. When we want to use make a contact between the available deep learning approach and the fluid dynamic area, it's required to determine a framework, which is here the Lagrangian framework. We have the data as a time series. The features are related to the variables, and these setup could be used on the LSTM, long short-term memory model. Since the data are large and we need to train these large data to the model, the parallel computing is essential. So HPC resources, it's required on the deep learning application in the computational fluid dynamic. And of course, we will investigate this feature on the GRU gated recurrent unit. Now let's talk about the experimental data. As we promised, we will have the practical example. Here we will start about this application. To run the deep learning model for the CFD, the first thing is a data set. As we said, data set for the turbulent flow must be three-dimensional in the actual condition to make it reliable and also applicable broadly. In this regard, instead of using data from the CFD simulation or starting to making CFD simulation in 3D, which is taking a long time to do that, and our focus was using the deep learning. So we focused to use experimental data, which is available from the laboratory. It's from our previous research in the turbulent flow. In this experimental data is a simulation of the strained turbulent flow, or we can say deformed turbulent flow. As you can see in this slide, in this experiment, there is a tank with 8 impellers rotating. They are in the corner, and they, with this rotation, they creating and generating the turbulence of the flow. So we have a specific turbulence intensity depending on the speed of these impellers. Then the location of the measurement of the data that we want to do, it's in the center of the tank. You can see on this sketch, it's 24.5 millimeter square. It's far from the wall to be sure that in this area it has a homogeneous and isotropic condition in the beginning. And then to extract the feature of the turbulent flow, we use the Lagrangian particle tracking, LPT, which is approach that's using the Lagrangian framework concept, following the particle and measuring its velocity due as a time series. And also another parameter also it could be extracted from this measurement, like the acceleration, and also with this calculation we can extract the vorticity, for example. Then this work has been done, and the flow seeded with tracer particle, which they have density same to the water, and the water, the fluid flow here in this experiment. When the impeller generated turbulence of the flow, on a short time, there are two circular plates up and down in this tank, as you can see in the sketch. They're moving toward in the center of the tank and making deformation to the flow. These similar to the straining of the turbulent flow, which happening in the many applications. For example, when flow passing an object, for example, flow passing the airfoil, passing a sphere, this straining is happening, and there is a location which is a stagnation point on this type of the flow. Also, when in the flow in the combustion, also in the combustion chamber, it's happening the same motion. So we can say it's applicable in some industrial application, also in the nature. There is a similar behavior of the straining turbulent flow. When the experiment has been done and the data is measured, for every performance, every experiment when it's done, 20 times measurement is happening. That means for every experiment, 20 times repeat is done, and the measurement taken from the experiment. Firstly, we had to check that the experiment and the measurement matching. Therefore, when we made the experiment has been done with a specific strain rate 4 and strain rate 8. We post-processed the data and we calculated the uh, strain mean strain rate from the extracted data, and it's remarkably match the theoretical mean strain rate. Therefore, the experiment was successful, and the measurement also matched the theoretical input of the experiment. Uh, and the main point is because this experiment is in the actual conditions, so we have 3D simulation. However, from the measurement, we use the two-dimensional measurement. That means we measured only x and y direction. We don't have measurement from the third direction. However, it doesn't impact the actuality of the data because it was experiment and 3D measurement, a 3D environment of the flow. Then we expect to capture all the information of the turbulent flow, and we can use this data for the deep learning. Of course, there are much detail about this experiment. It's available on the published paper from this work. There are many detail about the laser that we use and the camera. It's high-speed camera. It's measured 10,000 frames per second to be able to run this simulation. And also the post-processing of the data is take a long time to process the data and extract these properties to be used in this type of the application of the deep learning. Here we can see the presentation of the data. We can see the time, x location, y location, and v, which is velocity in the y direction. Particularly in our study, we designed an LSTM model and GROW model to predict every component of the velocity individually. That means when we have the 2D dimension, we can make a model for prediction of the velocity in the x and y direction individually. Then if we have 3D measurement, we can run it for the 3D without any impact or negative point. So it's able to run it with the different dimension. The data, as you can see here, the location x and y, they are function of the time, and also the velocity function of the time and the location. So regarding the designed model of the LSTM and GRU for these data that we explained from the experiment, we focus to make a prediction for the velocity in the x and y direction. Here is a presentation of the velocity component in the y direction. In the right hand side, we use 60% of the data for training and 40% for test. Of course, the validation for the training also available, which was 20% to be sure about the training. The green color is training, and the yellow color is the prediction for the LSTM, and the purple color is the prediction for the GROW model, and the blue color, as you can see, it's in some areas of the figure can be seen. It's for the actual data, and you can see how much the prediction matched the actual data, which mean the model it was successful. Also to check how much the training can help to make the prediction with high accuracy, we change the training with 80% and 20% for the test. This is the left hand side on this slide, and you can see again with the green color is the training, and the yellow color for the LSTM model prediction, and the purple color is for the GRU model. And here the prediction has a much more accuracy. You see, it's much more color, the blue color of the actual data. So this is the comparison between the LSTM and GRU, and we can see the result about to be similar. And so the GRU has a capability same to the LSTM. Here we are presenting the different of the performance of these two models. As we said, we use the training with 80% and 60%. However, for the computing, we use different categories. One time we use one node with one GPU, and in another setup we use one node with 4 GPUs. For the 80%, we can see the scalability of the GRU get higher than the LSTM. Mean absolute error is so close, and squared R2 also squared R also it's close to each other. When we have 4 GPUs, we see the LSTM scalability much better than the GRU. And regarding the mean absolute error and the squared R also they are same. When we use the 60% also, we can see these behavior is repeated. Then we can say when we use the GPUs, LSTM get faster than the GRU. But without GPU, GRU has a faster performance than the LSTM. This is from our test from the speedup for this application, which is reported in this paper. And so far we saw example how when we can apply the deep learning for the application in the turbulent flow. This application could be developed in many other real condition. For example, when the flow passing and the object, or when we are studying the flow around the airfoil in the aircraft. For example, in the airfoil of the wind turbine, there is a very specific issue. It's called leading edge erosion because of the airborne particle. When the flow passing the wind turbine, they're making some erosion when they hitting the surface of the wind turbine blade. So this application could be applicable. For example, if there is a data on this area, we can use this model to study how the particle hitting the surface and which area much more getting impact from them, and it lead to the erosion. So we can have a prediction and use it for the material science and reduce this impact. Also about the other application, we developed this model to use it on the some other same condition. For example, in the wind power industry also, there is some issues that could be resolved by this method. As we know, the wind power, the wind turbine, working with the wind speed, and because of the wind speed has a turbulent behavior, there is no understanding and prediction for the wind speed. So we need to know how long period of the wind could be predicted, and then use this prediction to have a prediction of the wind power production. For example, the wind producer who is owning the wind farm, they need to know the short-term or long-term prediction of the power production to be able to respond the demand of the power grid. And because of this shortage, it's very difficult to deal with the long-term prediction or even the short-term. This model could be used in this area, and we developed the model to be used in this area. Also, the another example of this application, currently hydrogen, one of the great green energy resource, which many studies ongoing to using the hydrogen. Recent studies show one of the great location to produce the hydrogen. It's the wind farm and solar farm. It's mean because when we wanna use create the hydrogen, we need to have the electricity, and if we use the electricity from the sustainable energy like the wind and the solar, it will be economically and scientifically feasible to make these application. Then prediction of the wind speed and prediction of the wind power will help to have a forecast for the wind speed and be able to arrange and schedule the wind power demand to be used, for example, on the urban area, on the power grid, and when we can use it for the hydrogen production. Here, this example about the wind speed, and this is, we can say, we can have this practical example of the deep learning model for the wind speed. Here, the data is measured from the borefeld location from the Icelandic Meteorological Office. In the borefeld, there are two E44 wind turbine installed for the research. And there are two type measurement of the data, 10 minutes time step and 1 hour time step. Here in this slide, we are presenting the wind speed from December 1995 to February 1996, and the another one is from December 1996 to February 1997. So when we look at the blue and the red figures here, we can say there is not correlation between them and no similarity. It has a random and non-linear, so we need to predict this. The idea is to have, for example, like this measurement for this year, and then try to measure the next period. For example, if we have the data until today, do we have to predict next few hours, next day? This is the idea. We use this data with this design deep learning model to make some prediction. We focus on the growth and let's look on the model and how it was working. Here also we were thinking to how use this idea, because in Iceland, this data are from Iceland. Of course, in the winter and the summer, we have different behavior of the wind. This is something about the event is called ghost event, which is you can see very some high value of the speed, which is make this fluctuation on this data. So we decided to split the data to seasons. That means if we can call it winter season and summer season, for example, and we're using the data by season to make a prediction. Because if we use the data, for example, from the winter to end of the summer, and we're expecting to predicting the fall, it doesn't make sense based off the data. There is not correlation between them. However, we didn't test that method. We prefer to use firstly the season data, use the season data and predict the next time of these seasonal data. From 1996, we have time step with 10 minutes, and from 2022 to 2021, we have data with 1 hour time step, and we apply this data with Go. uh, to make a prediction of the wind speed. Here you can see the first model, which is run with GRU. The time step here is 1 hour. The data set is 60% and 40% for the validation for the test. The model as mentioned show the square R is 0.71 and the mean absolute error is 0.059. And here you can see the blue color is the actual data from the measurement, the red color is the training data, and the prediction of the GRU is the yellow. And you can see how much they are matching. Of course, they are not matching perfectly, and as we can see from the mean absolute error and R2, it's not perfect prediction. We should mention in this model the time step of data 1 hour, and also the training is 60%. So we try to improve it. When we try to improve it, we use the data with 10 minutes time step. That means the training between the data is get a small time step. The data set 80% and 20% for test. The estimate of the model show the R2 squared R it's increased to 0.97 and mean absolute error it's reduced to 0.019. The changes is in the R2 36 it's increase and mean absolute error is 67% reduced. And you can see how much they are matching the training red with the blue and the prediction the yellow one how much matching with the blue one. So these here it's the application of the LSTM and GRU model we use for the turbulent flow. As we said, the first idea in this practical application was to design approach that could be used on the many similar actual condition. So we developed the model first. We use it on the experimental data from the laboratory, and then we used this model to area of the wind speed, which is applicable in the energy industry and can make the wind power producer able to have a prediction at least for short term or long term to predict the wind speed and then use this wind speed to predict the wind power production. There are some other ideas could be added to this method. For example, because the HPC system also is costly and it's required to make a prediction for the wind speed. The idea it's we have an idea that suggests okay for every wind farm they can have a the HPC cluster in their location and using the its power from the wind farm, so this make it completely green and sustainable, and using this HPC to make a prediction about the data also instead of using measured data, making online system as a software and the measurement with the online system coming to the software and making prediction for the short term. And this with this short term with few hours they will be able to measure for next days or next few days the power production, and this make the power grid is to know the production of the power and how respond to the demand of the power. And this idea also is connected to a smart power grid, which is part of the idea of the smart cities that is followed in the recent year in the many countries, especially in the European zone, and could be helped to run the smart grid in the smart cities. So if we want to present this idea in flowchart, as you can see here, we have the deep learning model, which was LSTM and GROW, and the data from the velocity measured. We need the HPC resources for the deep learning model, and then the target is predicting the wind velocity in following period. Regarding the HPC, we have ongoing research to have a setup for the hyperparameter optimization to make the to optimize the model and optimize the performance of the HPC, the speed up, which is could be helpful also regarding the energy and also the application of the HPC resources. Here we finished the lecture 11, part 2, and in the end there is a video. It's presenting the neural network train for the physics of the fluid and the smoke, and I suggest you watch this video and you see this application. Regarding the example, here we have this in lecture. The data are available on the published works, and if you are interested, you can look at them. Also, I can suggest you, if you are interested for the final project of the high performance computing course, and also if some of you may be looking for some data for the master thesis, our data are available for the wind and also for the turbulence flow. Maybe you want to use it for the deep learning or maybe some other physics-based model of the machine learning. If you are interested, feel free to contact us and we can provide you the data to use them in your research. So we will continue in the next lecture with another aspect of the fluid dynamic and HPC application. And thank you.